Hello, in this video we want to cover storm shelters designed with structural masonry. My name is Sam Rubenzer. I'm the founder of Force Consulting and the managing director. I'm a licensed structural engineer in the state of Illinois and a professional engineer in a lot of Midwestern states. I have my engineering degree from the University of Minnesota, my MBA from Marquette University. Here at Force, we've done a lot of different designs in masonry, in particular storm shelter designs and other designs, just helping educate the professionals across the country for how to design better with masonry. So for today, we're going to review the when and where do we need to design storm shelters, what is essential in storm shelter design, what are the different changes that you would make from, say, a typical masonry design or a typical building design if you're going to be designing storm shelters. And then we're going to take a quick peek at some of the different software tools that can help us design storm shelters more effectively. We also want to note that there is a new chapter in ASCE 722. I think that's now coming into play for different codes in different areas as they adopt the more recent IBC codes that reference ASCE 722. I just want to make note that Chapter 32 in ASCE 722 addresses tornado loads. It's a little bit different than what we're going to be covering today. It's not for storm shelters per se. It's just addressing minimum tornado loads for conventional buildings. But storm shelters actually provide even more protection and follow additional standards like ICC 500 and FEMA P361. So again, this is for main wind force resisting systems and components and claddings on the overall building, and that again, it doesn't cover storm shelters per se. But other things that we want to also make note of, if we're going to look at storm shelter design, we're going to review some of the basics for masonry design to certainly make sure that everybody is up to date on some of that. So it might be a review from some of the other videos, but we're also going to talk a little bit beyond what we've discussed in some of those other videos, which, kind of leaning toward maybe something that might be unconventional to increase strength of the overall shelter for masonry design. First thing to talk about is certainly all designs, including storm shelters. We really want designers using the actual available strength of masonry. There's been a lot of misconceptions through the years for masonry having a much lower strength than what they actually have available. So we've been encouraging people for a long time to use the actual strengths for block strength. And so really design-wise, we want to make sure that we're taking full advantage of that. And then certainly within the storm shelter designs, we maybe even go beyond what might be typically available to some higher strength elements. Just a really quick review within the code, within the Masonry Society Code 602, Table 2, really does cover the different values for block strengths that are needed. And when we use type S mortar, what the overall strength of the masonry assembly would be. Just a quick note that it is common to have an F''M of 2500, but again, with the shelter design, we maybe even go beyond that and go to a little bit higher strengths. Could be 3000, could even be 4000 PSI. We also do have structural clay that could be available for storm shelter design. Again, if we're looking at doing a shelter design, we maybe desire to have it look like clay, and clay might be available to do the design as well. The strength of clay being a little bit stronger than what the common concrete masonry would be. So again, we could have clay masonry that could have an F''M easily of 4000 PSI as well. Control joints affect the analysis of masonry design. That should be something that everybody's familiar with by now. Control joint locations are based on a relatively new guide from the CMHA, the Concrete Masonry and Hardscapes Association. They have a Tech Guide 9-25, which is kind of a replacement for some of the older NCMA documents. They cover reinforced walls, the fact that you don't want to have movement joints at opening edges, and you certainly don't want to have that with shelters. For most openings, you can move the joint at least 2 feet away. Unreinforced walls, which again we don't have here, that's where we put the movement joint at the edge of the opening. So we're almost bringing it up, not because we'd want to consider it, but just know that the only time that you would even put a movement joint at the edge of the openings would be in an unreinforced wall, and we certainly don't have that in a shelter design. But then there's also options for foregoing control joints, movement joints in our shelter design if we add enough horizontal reinforcement. So that might be a very useful option if we're trying to maximize the overall strength of the storm shelter. Again, it's very, very important to remember that it's mandatory for all masonry walls, and it's even more important that we locate where movement joints go within a design. And I've been actually encouraging designers to also specify where we definitely do not want to have movement joints. So if we had a shelter design, we had elevations of the design, maybe what we do is we highlight that the entire wall should not have any movement joints if that was the choice that we were choosing to make for our design. So again, we have different options. They're all kind of laid out by, again, this tech guide 9-25, which is similar in the information that was in all the previous NCMA tech guides, 10-1, 10-2D, 10-3, or 10-4. So really a lot of different guides that are out there, but again, the one that we would want to use now is the one on the far left. So again, within that guide, it points to different types of options that you have for adding certain levels of joint reinforcement and control joints. So there's kind of a balance. The less horizontal reinforcement, the more control joints you would want, but the more horizontal reinforcement, the less control joints that you need. So we'll talk about that a little bit more, but again, this guide kind of walks it through. Again, the minimal horizontal reinforcement and regular movement joints, that's when you have the joints at 25'4" or 1.5 times the height, and then again, a few other criteria factors there. But again, we have a second option and even a third option. A second option where we add enough horizontal reinforcement maybe within bond beams and don't have a need for control joints. Or we can add a combination of bar reinforcement and bond beams and horizontal joint reinforcement and not need, again, those movement joints. So these are the second and third option are really nice options to consider for shelters. So here you can see the table that's provided within the guide for the bond beam reinforcement that you could use to not have to put in a control joint. So I think it's even more important to consider maybe the option of the combination of bond beams and joint reinforcement. Because storm shelters are going to be solid grouted elements, providing enough horizontal reinforcement with just bond beams does require quite frequent bond beams. So if we can engage both joint reinforcement and bond beams, then we can have these bond beams space out a little bit more regular spacing. So again, in this example, you can see a table that we put together where we look at a 12-inch wall thickness. So that could be a very common storm shelter wall. That would be solid grouted. Could use joint reinforcement, 2 9-gauge wires at 16 inches on center, in addition to a bond beam at 40 inches on center with 2 number 6 bars. So that would be kind of a very typical storm shelter design. And so you can see how within this guide, how we come to that approach and come to that level of reinforcement. So again, some really quick illustrations for what that looks like. Again, the standard minimum horizontal reinforcement with regular control joints, or the equivalent option is the increase in horizontal reinforcement and not needing to have movement joints, which again, also comes into play if we do have some openings. Again, shelters can have openings. We certainly need to have a very well-designed shutter system or system to prevent those walls from compromising those openings. But again, the masonry design is also going to change a little bit. We'd have some continuous masonry lintel elements over the openings and continuous sill elements, some combination of horizontal reinforcement to again, not need to have any movement joints. We have a few different things that are kind of in play here. I mentioned lintels. If we look at masonry, lintels would be definitely the option we would want to go with. It's going to create the most robust elements for spanning an opening. We certainly have the right tools, the finite element analysis tools that you can use to make sure that you understand the behavior of the masonry lintels over the opening. So again, we understand that a masonry lintel is going to act similar to a fixed end beam. It's going to be connected to the wall elements on each side, kind of a coupling beam between the two different wall elements. So again, really kind of maximizing the overall potential for your wall systems when you have masonry lintels that connect elements on each side. And again, finite element analysis is going to be an important part of the solution here. Again, making sure that we can see the entire forces on all the buildings. We can see kind of continuity effects and complicated load paths or significant load paths and how the load's going to move through the model. We get a good visual representation, and then certainly we can make revisions relatively quickly. So again, looking at a typical model that we might put in, or a shelter that we might want to put in, just using finite element analysis, so we can really do a nice evaluation for the stresses and forces within the elements, and you can kind of see how we're approaching that here, both the windward, leeward pressures, and maybe some sidewall pressures as well. So those are just going to be some really quick overview or some brief tips of design of masonry and things that we definitely want to make sure that we remember, and we'll include that, some of those different elements within some of the examples at the end. So storm shelter provisions, some of the different provisions that we're going to cover come from ICC 500 or the FEMA document that I referenced earlier. So we're going to reference back to these a few different times within the presentation. Some of the essentials of the storm shelter design, certainly going to cover some code documents and some of the different particulars within those documents. We're going to look at wind speeds, wind load calculations, wind-borne debris, how we'd modify maybe from a typical design to what we'd want to use for a shelter. Look at some different options, continuous load path, and then at the end we'll cover some examples. So again, in IBC, you can see that there's different additional other applicable requirements to the code. Storm shelters can be constructed in accordance with ICC 500 as stated within the code. Within IBC 2015, we had this section applies to the construction of storm shelters constructed as separate detached buildings or constructed as safe rooms within buildings for the purpose of providing safe refuge from storms that produce high winds, such as tornadoes, hurricanes. Such structures should be designed to be hurricane shelters, tornado shelters, a combination. So we have a lot of different load requirements that are certainly kind of within, those different types of elements. So ICC 500, adopted since IBC 2015, mandates storm shelters for certain geographic regions and certain building usages, critical facilities, emergency stations, Group E occupancies, so schools. Obviously, we want to have some good shelter in place options for schools where we have a lot of children. Locate storm shelters within the building or maximum distance not exceed 1,000 feet. So certainly want to make sure the shelter is accessible to everyone. And then IBC 2015 published in June 2014 and adopted by various states and local jurisdictions. So I'd certainly recommend understanding what's in the provisions, even if it's not even adopted by different local jurisdictions. I think there's a lot of very good, important information that we can utilize here to definitely educate areas that maybe don't reference and utilize, some of these documents or some of the most recent changes. And IBC 2021 Section 423 states that the shelter design wind speed is 250 miles per hour per ICC 500. The following occupancies, again, have a storm shelter constructed, critical emergency facilities, Group E occupancies, so on and so forth. And you can see the sections there. New additions from ICC 500 Storm Shelter Standard and FEMA Safe Room Guidance. So we have some more recent changes as well. So FEMA P361 is going to be a document providing guidance for safe room design. And it is important to note that there hasn't been a single reported failure of a safe room constructed to the FEMA criteria. So again, we know it works. Unfortunately, it's been tested, right? We've had high wind load events that have occurred, and we know that when we follow these procedures, we have success. And so we certainly have confidence in following that standard. And certainly we'll keep making some updates as well. ICC 500 is a standard for storm shelter design constructed, adopted by reference by the IBC. ICC 500 2020 is referenced by IBC 2021. There's even more recent IBC 2024 now as well that we need to consider the updates and provisions to that as well. There's some very nice guides we talked about earlier, about some of the different guides that are available for masonry design from CMHA. Well, they also have a guide for masonry storm shelter design. And so there's an earlier reference to that same guide. The National Concrete Masonry Association, NCMA, provided a storm shelter guide since 2015. So those are very, very useful documents, documents that I use and reference still to the shelters that I look at and design to this day. Some of the different terminologies that we want to make sure that everybody's aware of. So according to ICC 500, a building, a structure, a portion of thereof is constructed in accordance with ICC 500 for the purpose of providing safe refuge for storms that produce high winds such as tornadoes and hurricanes. So pretty straightforward stuff. Purpose of the standard is to establish a minimum requirements to safeguard the public. So we have residential storm shelters that serve occupants in dwelling units not have an occupancy load exceeding 16 persons, or a community storm shelter, really anything that's not as small as what you'd have in a residence. We also have FEMA Safe Room, where it's a building, a structure, a portion thereof constructed to provide near absolute life safety protection in accordance with FEMA P320 or FEMA P361, where ICC 500 is reference standard. Also specified recommended criteria that is slightly more conservative than ICC 500. And why is this so important? We know that this is really important across the entire country. We can look at all the different areas that the code is going to try to increase and show the increase in wind speed. Certainly in the places that I call home, I have never really thought that tornadoes were as significant as some of the areas in the South. There certainly is the, area in Oklahoma and Missouri, Arkansas, that certainly have significant events and maybe more frequent significant events. But I think it's really good to look at the recorded events to see that, when we define the region as really all across the central United States from north to south, you can see that there's been a lot of events in the Midwest, in the Minnesota, Wisconsin, Michigan, Iowa, Illinois, Nebraska, all of those states, not necessarily places that I think of when I think of, a high risk of tornadoes, but you can see that based on the history, based on all the different events, and I can look at that from several different sources. You can see that really there's high wind events all throughout the central part of the country. So that's what really kind of comes into play as ICC 500 and IBC have determined what zones. Zone 4, having that 250 mile per hour wind, is actually quite a large region. That covers more than half the state of Wisconsin, plenty of Minnesota, all of Iowa, and then certainly dipping into Nebraska, Kansas, most of Oklahoma, good parts of Texas, and then stretching to the east. So we know that we have to design our shelters for 250 mile per hour winds in these areas. So again, is it just a really quick example? So maybe a typical wind speed might be 115 miles per hour versus a wind speed of 250 miles per hour. Doubling that velocity is certainly going to make the pressure 4 times greater. And so certainly that's a really important factor to remember. We're really dealing with 4 times the pressure loads on our structures when we're trying to design for shelters. So that's fairly significant. So really looking at the FEMA document, residential safe rooms shall be designed for 250 miles per hour as well. One of the other things that people reference when we talk about wind speeds and events, we can see that the EF scale, EF 0, 1, 2, 3, 4, and 5 over 200 miles per hour. So you can see some of the different scales there and some of the different wind speeds. So we know that we have these events, and we know that we have them of significant wind loads across the country. So ICC 500 Section 304 wind load calculation. We have a kind of a summary. Use ASCE 7 ICC 500 modifications ASCE 7 wind load procedure can be used, directional envelope, simplified methods not to be used. But then we could also see the directionality factor of KD of 1.0, exposure category of C, topographic factor, we can keep that at 1.0, and the enclosure classification. Do we have an enclosed or partially enclosed? And really kind of looking at this and trying to understand, some of the differences. Once you have a partially enclosed building, certainly the internal pressures go up significantly. And I think when we're looking at a shelter design, we're looking at, both the windward, leeward forces, side forces, in addition to the internal pressure. Certainly recognizing that a little bit of a compromise for the building envelope could certainly increase significantly the amount of pressure that you'd have in a building. So again, if we're looking at trying to design to the maximum wind loads that a building could see, that's where we're going to start to lean towards the partially enclosed. So total area of the openings in a wall receives positive external pressure exceeds the sum of the areas of the openings and balance of the building by more than 10%. Total area of openings in a wall receives positive external pressure exceeds 4 square feet, or 1% of the area of the wall, whichever is smaller. So the enclosure classification, again, comes into play. So again, if we have any compromise or we had any breach in the building envelope, really that's where we're looking at increasing the enclosure classification to partially enclosed. So again, for most typical buildings, we're going to be looking at the plus or minus 0.18. So again, moving then to partially enclosed is going to increase the coefficient to plus or minus 0.055. Other elements that we have to understand is wind-borne debris. So certain the type of construction that we use has to be able to handle some of the different elements that are going to be projectiles and flying through the air. Certainly we have different types of members that are, again, for structures that are compromised, that become part of the debris field, is going to be important elements to look at. So here you can see the different types of debris size that we have to consider, and how that debris would potentially affect the overall designs. So for wind-borne debris, how do we design for that? Really, we have to do some testing. We have to look at the different systems that we are going to be using in our designs. ICC 500 has some requirements for what that looks like. So for this test, it's going to be an impact test of a 15-pound 2x4 traveling at speeds according to the table. So according to the table that you can see here on screen. So again, if we go to look at our different wind speeds, and again, we have the different areas on the map that we can reference. If we go all the way down to 250 miles per hour, again, that large, significant central part of the country, the missile speed shelter impact at this shelter impact surface would be 100 miles per hour for vertical surfaces and 67 miles per hour for horizontal surfaces. So 15-pound 2x4 flying at 100 miles an hour at your structure. So again, we do some testing. We look at what the impact and test results would be on the different elements. We've looked at for masonry, partially grouted, solid grouted. We look and see what the impact would be at different elements and joints within the design. So we do the test. We fire the elements. We fire the 2x4s with this big 2x4 cannon. At some of these different elements, we look at what the say a cavity wall would look like. So again, if we have clay elements that are just veneer, that are unreinforced or mostly unreinforced, what happens to them, and then what happens to the concrete masonry wall behind? Certainly it could be a reinforced clay element as well. So again, with the 2x4 cannon, you can see here, pretty sophisticated piece of equipment. We can again start to fire some of these elements at the wall. You can see that mostly the unreinforced veneer is not providing much protection. You can see that it's kind of crumbling in the overall design. So we know that wind-borne debris, all openings must be impact protected. So openings can certainly be the weak link in a building envelope. So any rectangular penetrations larger than 3.5 square inches, or circular penetrations larger than 2 1/16 diameter, considered to be openings that have to be protected. So again, we're trying to keep the building envelope as intact as possible for our designs. So some other modifications to ASCE wind load shall be based on ICC 500 requirements for wind speed. Again, we have modifications to roof live load per ICC 500. And then strength design, we want to make sure that we consider live load reduction is not allowed for a storm shelter design. Place of assembly, probably high amounts of debris live load that could be on a building. Other roof live load modifications, we want to make sure that it's 100 PSF for tornado safe rooms. So we have 100 PSF live load that we have to consider. But then we also have the impact loading from a collapse or laydown. Really what that looks like, it can certainly vary depending on project to project, what the actual impact force would be from the collapse of an adjacent facility is really, really a significant design element that we have to consider. Obviously, if you can design your shelter away from elements that could fall on top of it, that would be certainly beneficial. But certainly considering that part of the design is going to be extremely important. Just a few other changes from in ICC 500 2020, storm shelters, owner's responsibility to maintain the shelters and ensure they're in good working order. Obviously, we're going to have a lot of different moving parts and pieces to a building that's going to be used, making sure that everything is going to be maintained in terms of doors and windows, and everything is certainly going to be in good working condition. Annual evaluations of the shelter envelope and impact protective systems needs to be considered. Addressing leaks in walls and roofs if they appear, and careful evaluation of walls below grade shelters exhibiting cracks or signs of water infiltration would be really important. ICC 500 2020 Section 109 requires a third-party review for community shelters with an occupancy load of 500 or greater, shelters in schools, occupancy load greater than 16, shelters in risk category 4 structures. Other significant changes to ICC 500 2020 for structural engineers, structural loads and debris hazard updates. So the tornado wind load contours remained unchanged from previous versions. 2020 version included updated hurricane wind speeds, incorporating climatology data through 2018, which parallels some of the recent developments in ASCE 722. Roofs designed for extreme roof live loads, 100 PSF for storm shelters, 50 PSF for hurricanes. Consider vehicle loads for following the applicable building code for obviously for the below grade shelters. And then floor live loads for tornadoes shall have assembly occupancy live loads. Floor live loads for hurricanes should be the same as normal occupancy for the space. Then ICC 500 2020 Section 30503, more explicit language for laydown and falling debris, explicitly addresses laydown and falling debris hazards. Again, I still think that there's a lot of engineering judgment that needs to go into those type of elements. Expanded to include some criteria for determining if designers need to consider falling debris and the shelter design debris and hazard are present in taller adjacent buildings. So again, depending on the complexity of your site and what might be next to it that could be compromised, is going to be really important to look at. But then a must-use minimum factor of 2.0 to account for the dynamic effects of a falling debris simultaneously with uniform roof live load. So again, we're trying to get to addressing some of the impact loading that you would have from some of the adjacent elements that could be falling down. ICC 500 shelter concept, classroom as a shelter. So we have some wall windows within walls that need to be considered. So shelter walls designed for both missile impact and shelter wind loads. We have interior walls, partitions or structural, no requirement for missile impact, obviously if they're inside. We have to have doors and windows that are certainly rated, and then connections from those doors and windows as they attach to the wall elements that they're within. Or you could have, in this case, an expansion joint is provided between the corridor and the shelter. Shelter foundations can be sizable. Separate shelter minimizes conflict with existing foundations. The shelters could also be a freestanding structure addition with physical connection to the existing school, which allows for safe access to the shelter during the storm. So we have a lot of different options that we can consider there for the overall design. Some of the structural system options for the roof, again, we have to be capable of resisting the high upward, downward pressures, and then the debris. Again, the 2x4 for the horizontal surface, I think it was at 67 miles per hour. Walls are going to be a little bit different, so hardened walls to resist the high pressure loads, but then a higher 2x4, 15-pound 2x4 flying at 100 miles per hour to our different wall systems. And then we also have to take a closer look at foundations, making sure that they can resist the uplift forces that you'd have for the shelter. So some of the structural and building envelope characteristics. So the structural systems are certainly designed for the higher wind speeds, corresponding to higher wind pressures. Also larger, more energetic wind-borne missiles than conventional buildings. So that's pretty obvious. The envelope, the walls, the roof, the door assemblies must be able to resist all of the different wind-borne debris in addition to all the different pressure forces. So with that, I think it really kind of boils down to what are the different types of structural system options that we look at. I think hardened concrete wall options are usually going to be the best systems to consider. Walls of either masonry, precast, or tilt-up certainly would have those attributes for design. You could also do a cast-in-place concrete wall as well. One of the unique attributes, I think, of masonry relative to, say, either precast or tilt-up walls is that the fact that you can build the walls to a larger area. And I think that that is an important aspect of what you can do either with cast-in-place or with concrete masonry or clay masonry elements, is you can build to a larger element, which is going to really reduce the overall force that you would have to put on it. And if you really think about that, really reduction in force is really get into the fact of, the whole system could then be responding to the wind load. So if there's pockets of pressure that are a little bit higher in more concentrated areas, that can be dissipated by the fact that our overall elements are going to be really working together in unison as kind of one monolithic element, instead of having a lot of different parts and pieces that might be loaded by again, some of those higher pressure concentrated loads in certain areas. So designing to walls higher than or larger than 700 square feet can use main wind force resisting systems. So something that's 22 feet long and 32 feet high, or 44 feet long and 16 feet high, gets to kind of that overall area that I think, again, addresses the utilizing the entire system together to work together as kind of that one monolithic element, instead of having these smaller elements trying to pick up some of the higher stress forces that could happen for buildings. Other options, certainly if there's a consideration between classroom wings and gymnasiums, I think a really quick example is just looking at the overall demand. For gymnasiums, we already talked about how 2 times the wind speed gives us 4 times the load. But if we also look at the demand on a wall, 2 times the span is going to give you 4 times the moment. So a gym storm shelter is going to have 4 times the load, 4 times the moment. That's 16 times the demand on those elements. That could be potentially twice as high as, say, a classroom wing. So when we talk about why it might be really important to consider classroom areas of a building versus a gymnasium, this is one of the main examples that I would use in trying to educate a client as to why it's way more extreme in a gym. Now, maybe that ends up being the space that is selected, but at least everybody's going into it with foreknowledge of what the overall demand would be on gyms versus, say, a standard building, standard design. The other really important parts that we have within these guides is looking at a continuous load path. So making sure that we have vertical load path continuity between whatever the roof system is through the beam elements that you have for the roof, then down through into the masonry walls, which again, that reinforcement attachment to the masonry, then the connection of the reinforcement, the lapped reinforcement, the different couplers that you could use for reinforcement to get the load all the way down to the foundation. So it's going to be really important elements to consider. And then maybe the foundation needs to have some ability to grab additional soil load if we have significant uplift forces on the foundation, or grab additional things that have weight, right? So roof weight helps, reduces the net uplift. So if it's heavy enough, compression on walls could be really nice, but even if you have some tension, making sure that reinforcement is lapped sufficiently, or couplers are used for the wall elements. Connections are going to be really the key to make sure that you have that continuity in the load path. What does that lead to? That does lead to significant amounts of reinforcement. If we look at the amount of reinforcement that you could see here used in this shelter for what's a 12-inch masonry wall, and then some of the reinforcement and the dowels that happen at the roof line. Again, 12-inch masonry, we have doubly reinforced walls. We have significant amounts of reinforcement that's doweling into the roof areas. So really it is all about load path and connections, making sure the foundations of the wall, we have fully developed, lap lengths, not just, small dowels. We need to have fully developed dowels that gets that force down into the foundations, so that the foundations can, again, grab more load if we need more load for uplift design. We have wall to roof, that bond beams and anchorage, making sure all of that reinforcement, again, gets attached and the forces flow through some of those different elements that would be much different than standard. Doors and windows, how they connect and how the connections must be into fully grouted element and elements to make sure that we, again, have the full capacity of all of the different elements connecting doors and walls to, again, protect that envelope. Veneer to structural width, certainly that's going to be important. If both are used for impact resistance, certainly looking at increased connectors for the veneer connection, and maybe even a structural veneer, so that you can have, again, could be grouted solid, could be part of the overall solution, and not just part of the debris field. Some different notes on foundations. We have safe rooms that must be installed on foundation. It has to be designed to resist all of the loads. You can see some requirements for reinforcement for slab on grade for these shelters. And then obviously, these are just some minimum requirements. Certainly you have to make sure that you check the loads and the overall design of the foundation. One of the really important steps of the shelter designs is making sure that you have it peer reviewed. Both FEMA and ICC 500 require peer review when the community shelter is designed for more than 50 occupants. Storm shelter is an elementary, secondary, or daycare center, has an occupancy load of greater than 16. Or if the storm shelter is in a risk category 4 essential facility. Peer review must include all the different chapters of 3, 5, 6, and 7 of ICC 500. Report must be signed and sealed. Peer reviewer must be an independent registered design professional. So obviously, very important to have that new set of eyes looking at all the different design items. Special inspections considered to be are for construction as peer review is designed. So certainly special inspections are extremely important to make sure everything gets built in field according to what the design documents illustrate. Construction documents should be prepared and maintained for safe rooms for both residential and community. Per ICC 500, they are required by the authority having jurisdictions. So some of the different requirements for construction documents, a statement indicating that the wind load conforms to the ICC 500. We have wind load criteria that must be defined within the construction documents that we use for the shelter. Minimum foundation requirements, Shelter installation methods, including anchor locations, minimum required capacity per anchor, and then documentation showing the shelter envelope must meet pressure and missile impact test requirements. Obviously, that's going to be important to use approved systems. We need to have a quality assurance plan for these designs, both for the main wind force resisting systems, connections from these systems to the foundations, wall connections to framing and diaphragms, foundation design, wall cladding and its connectors, and then the shelter envelope components, fabrication, installation to meet the missile impact test requirements. So making sure all the different systems are up to standard and they're all well connected to each other. And obviously all of these are going to be important. So just a really kind of brief overview. Obviously looking at shelter, there's a lot more than just the structural design, but 5 square feet per person. You need some sanitary, you need some bathrooms available for the shelters. You need to have a separate source of power to provide some emergency lighting. There's a lot of door and window requirements. And so obviously as engineers, we need to make sure that we're having a good understanding for what all these systems are as well, and how all of them, some of them need access and holes and need to have conduits through some of our designs. So certainly understanding what some of those impacts would be as well. So next we're going to turn to some different design examples, just look at some of the different forces and stresses and loads that you have, sample wind load calculations that we have for a design. Again, we talked about how much higher you would have for shelter design. If we just look at what the overall pressure forces would be for typical wind loads for a building, again, laying out all the different wind speeds and internal pressure coefficients, so on and so forth. So something like 23 pounds per square foot might be kind of a standard load to design for. Now, if we jump to looking at the 250 miles per hour load, certainly that's going to be jumping up quite a bit for the overall pressure force that we have to design for on a building. So you can see up to 130 pounds per square foot for the building. And then if we start to look at some of the different components and cladding pressures that you have, how those even kind of start to get up higher and higher. We're up around 140 pounds per square foot for some of the different elements design-wise. Almost up to 200, in fact, if you have a small enough element that you're designing for. So again, the enclosed or partially enclosed is going to be a really important set of criteria, looking at some of the different changes that you'd have there. And again, you can see the wind speeds and pressures jumping up even that much more for the overall design. So you can see what the different areas would look like, some of the different coefficients that are used, some of the different areas of the different components. And then here you can see some of the different pressures that are required to be designed for as we're designing some of the smaller elements in design. So anything that we can do to increase the overall size of the element so that we can, again, equalize that pressure a little bit across the areas so that we can have elements that are working together is going to be really important for the overall design. So looking at a really simple example for a gymnasium, again, 30-foot high walls. We have it located in seismic design category D. So we know that we already have pretty significant reinforcement requirements, load demand requirements, but a shelter is going to be, again, even that much more. So we're going to design it for 250 miles per hour, that partially enclosed pressure coefficient. We have the heavy loads that are on the system already. We have 100 PSF dead load just because of the 8 inches of concrete, and then we have the high live loads. So you can see some of the different forces that we're imparting upon the overall system, and then you can see some of the stresses that are being calculated for some of the windward, leeward sections of the design. Again, looking at the overall control joints and openings for this design, we looked at making sure that we minimize the amount of control joints. We really wanted to make sure that those movement joints are away from the openings. Again, there's some really good reasons why. Obviously, these are going to be solid grouted and reinforcement in every cell. So we know that we have the reinforcement there to prevent any cracks from occurring at openings. But also getting those movement joints away, we know that we can significantly increase the overall capacity of the walls. So that's going to be really important. We don't also want to make sure that we don't add too many joints. We don't want to drop that area of the wall down below 700. 700 is kind of a nice criteria for main wind force resisting system where wind pressures and forces kind of average out. So it's kind of a important threshold to kind of keep in mind. But then also other things that we want to consider is maybe even eliminating some joints. So we'll look at some of the other structures that we actually did that for in the design. So the overall final design, we had 12-inch concrete masonry and F''M of 2,500. Design-wise, we used Type S mortar, grout of 3,000. You can see that we had reinforcement that was pretty significant around much of the building. We had one number 6 at 48 inches on center for horizontal reinforcement that we used for the design. Vertical reinforcement, we had 2 number 6s at 8 inches on center. We had the same reinforcement within the corners of the building where we had, again, increased some of the pressure. Within the shelter, we also had some shorter walls where we, again, kept them grouted solid, but we could drop down some of the reinforcement, as you can see on screen. For some of the areas that with the openings, we can see the amount of reinforcement that we have, 2 number 4s, 8-inch high masonry lintels around some of the smaller doors. We have some larger lintels around double doors where we'd have 1 number 6 bar top and bottom, 24 inches high. But again, keeping the overall elevation to have movement joints away from the openings. This is going to, again, give us a much more robust, much stronger system. So you can see some of the different reinforcement that we had for this overall gymnasium design as a storm shelter. Again, looking at a simpler situation where we actually could use a classroom wing. And again, it's going to be a lot lower overall demand on the design because of the shorter walls. One of the other things that we did here is we eliminated the different movement joints that we had between different elements so that we make sure that we increase the overall capacity for the elements to work together. We really minimized the parapet for the design and obviously solid grouted for the impact resistance. So again, you can see what some of the different reinforcement requirements would be for the design. We had a 12-inch concrete masonry design. Typical reinforcement would have been 5 at 40 centered. Edge reinforcement would have been a little bit higher. Or we could go to an 8-inch concrete masonry design for this classroom with 5s at 24. Again, grouted solid edge reinforcement that would be a little bit higher for the overall design. And then another example that we've recently completed, this is a community shelter pavilion that's utilized. You can see actually that looks a little bit non-standard for a shelter, relatively large openings, and those openings did have some very significant heavy shutter doors that were actually designed for them, but then connecting those doors to all the different elements around and reinforcing. So even though this is a single story, this is also a 12-inch design because of some of the overall sizes of the openings that are considered for this element. But we laid it out, detailed all the different reinforcement, had that continuous load path all the way down to the foundation for this storm shelter design. So again, in summary here, we're going to wrap up with a couple slides on the summary of the essentials of design. Again, understanding what the different blocks, mortars, and grout that you're going to be using. Use Type S for structural. Use a standard block strength that's going to be whatever is available, or consider a higher block strength. We just helped the designer make that decision to go to an F''M of 4,000 last week. He had a pretty high demand for the tall walls and loads that are going to be on his shelter. So discussed going to an F''M of 4,000. Really kind of looking at and evaluating your masonry lintels and having some discussion with the overall amount of horizontal reinforcement that you want to use, potentially eliminating control joints for your design, or at least minimizing them, and then kind of what the overall load impact would be for that. So again, some of the different, single story, a minimal parapet is going to be kind of an ideal situation for a shelter because of some of the different things that we talked about today. The high strength masonry, no control joints, masonry lintels are really necessary to ensure the greatest capacity for our masonry storm shelters. We certainly want to track all the different code modifications for wind load, roof live load, lay down loads on a structure, ensure some of the different load path from foundations continues all the way through the masonry walls and connected to our heavy roof systems. And then some of the different softwares that you could see that we utilize today, Tekla Structural Designer and TEDS is going to be a nice finite element analysis solution. We've also utilized RAM Elements in their masonry design, or RISA 3D in some of their designs. So with that is going to be the conclusion of the presentation today. Certainly, if you have any questions, you can always reach me at sam@forceconsulting.com. Thank you.